This video is on the course of representation theory, and we are in the chapter of group representation. So this video begins with a definition. We define what a unitary representation is. Let V be an inner product space, so we don't have only a vector space, but this vector space as also an inner product space. So phi, taking from G to the general linear group, is said to be unitary if phi of G, our representation, is unitary for all G in the group. So another way to say this is, as you know, unitary matrices, they preserve the inner product. Okay, so we can say that the inner product of phi G of V, inner product with phi G of W, equals V, the inner product of VW for all V and W in W. Okay, so in other words, we can see this phi as if it was a mapping from the group G to the unitary group. Please check the previous video for this unitary group concept. So for all n, for all integers, the set of is the set of n by n matrices under matrix multiplication. So all matrices under matrix multiplication, they form a group, and this group is called the unitary group. Okay, where all matrices are unitary, and a unitary matrix is a matrix that is the transpose is the matrix is equal to the conjugate transpose. Okay, so so these matrices, they have complex entries, right? So what we are going to do here is we are going to identify the general linear group of 1 by 1 matrices. Okay, so this, at the end of the day, this is nothing else than complex numbers without the zero. Okay, so we pick a number Z that is, and complex numbers. Okay, we say that this number Z, this complex number Z, is unitary. We say that this Z is unitary if we look at it as a matrix. Okay, but we say that the number is unitary if the conjugate equals the inverse. Okay, so this is the same as saying Z times the conjugate equals 1, right? But this is exactly the same as saying that the absolute value of Z is 1. Okay, so in a certain way we are in the unitary 1 by 1 matrices group. Okay, this is the unitary group of matrices 1 by 1. Okay, so what is this? This is nothing else but the circle. Okay, where Z is an element from the complex numbers, right, such that the absolute value of Z equals 1. Okay, so this is the unit circle in the complex. Okay, So this is, at the end of the day, this is a one-to-one, or a one-dimensional, sorry, not one-to-one, also one-to-one, but a one-dimensional unitary representation. Okay, so let us say this phi is taking from G to the unit circle. Okay, if we identify this unitary group, we ended up getting to the general linear group. Where did I write this? Oh, here. Okay, sorry. The general linear group of 1 by 1. So general linear group of 1 by 1, that's the same as complex numbers without 0. Right. So at the end of the day, we are doing, so the unitary, we could write the unitary representation this way, and we can also write the unitary this one dimensional, because this t as dimension 1, one dimensional unitary representation. Okay, and this is of course a homomorphism. Okay.